So this question, if integration 0 to x 2x f square t dt equals to integration 0 to x 2 times f x minus t dt whole square, f1 is 1 and fx is a continuous function for x is greater than 0, n is a sequence and the sequence is given by this recurrence relation, n plus 1 equals to n plus root over 1 plus n square. A0 is 0. Fx is an increasing function. Then you have to find out the value of greatest integer function limit n tends to infinity a suffix k whole divided by 2 to the power n minus 1, where k is f n to the power root 2 minus 1, which is equals to which one? These four options are given. This sum is actually comprises of three sub-sums. So this is the first one, and the second one is you have to find out the value of tan inverse 1 by f prime 1, and we have to prove that f of n to the power root 2 minus 1 is n. Big sum. And what I will say is, if you solve this problem, I can assure you that you are going to revise the whole calculus almost, because it comprises of definite integral, differential equation, because we have to solve for fx. So differential equations will come. Recurrence relation is given, inverse is given, monotonicity is involved, everything, almost everything is involved in this question. So what I will suggest you, pause the video right now and please give a try to this sum. And if you can solve it, it's okay. Even if you cannot solve it, come to the solution and then check it. And one request is there, don't skip the video. Otherwise, if you skip some part of this class, you will not get the actual flavor of this sum. So let's start this sum. So we have been given, the first thing is that integration 0 to x dt equals to, I can take this 2 outside, so it will be 4 integration 0 to x f of x minus t dt whole square, right? Now, at this place, f of x minus t is there. So I will use the King's property. So we are going to have integration 0 to x f of, in place of t, I am writing x minus t. So you are getting f of t dt whole square. That's it. Okay. I have simply used the King's property. Now, one thing I can also do, I can take this 2x outside because it is a function of t, so I don't need to write x inside the integration sign. So 2x is outside, it's basically f squared t, okay? My prime motto is to find out what is my fx. That you have to find out somehow whether. So now, let me apply Newton-Leibniz theorem. So let me differentiate both sides with respect to x. Differentiating both sides with respect to x. So what you are getting? This is basically a product rule. So first function constant, integration of the second function, ddx of the second function, I'm sorry. So this is f2x plus 0 to x f squared t dt. And the right hand side we are getting 4 into 2 integration 0 to x fx, just 1 second, integration 0 to x ft dt into fx. Okay, so this 2 and 2 goes off. Let me just write, now let me denote integration 0 to x ft dt by capital A. So we can write this thing as x is equals to 4 times fx, and this is your A. Now, I am trying to replace this one from this equation. So from 1 we can write that integration 0 to x f squared t dt is 2 over x a square. So if I replace this in this equation, in equation 2, we are getting x f square x plus 2 over x a square is equals to 4 times fx into a. So that gives us x square f square x plus 2a square equals to 4xa fx. Now this gives us x square f square x minus 4x fx into a plus 2a square is 0. So you can write this thing like x fx whole square minus 2 times x fx into 2a, and let me write this thing as 2a whole square, that is equals to 2a square. Am I correct? Okay, so from here we are having x fx minus 2a whole square is 2a square. I'm writing it here. So we are actually having x fx minus 2a is plus minus root 2a. So x fx is plus minus root 2 plus 2a. So from here we can write x fx is, if I take plus minus common, it will be plus minus 2a, right? So from here we are getting a is x into fx. So if I rationalize, what we are going to have? Root 2 minus plus 2, that gives us 2 minus 4 x fx. So minus plus root 2 minus plus 2 divided by 2 x fx. That actually gives us 1 over root 2 minus plus 1 x fx. Clear? Which is same as 1 plus minus 1 over root 2 x fx. And what is the value of a? It is integration 0 to x ft dt, which is equals to 1 plus minus 1 over root 2 x fx. Now, let me differentiate both sides with respect to x we get. by using Newton's Leibniz theorem, fx equals to x f dash x plus fx. So that gives us 1 minus 1 plus minus 1 over root 2, 1 plus minus 1 over root 2, x f dash x. Is it clear? So now this thing will give us fx. It is just a simple calculation, nothing else. So this is minus plus 1 over root 2 equals to 1 plus minus 1 over root 2 x f dash x, right? Let me just copy this thing in our next page. So we are having this. So from here we can write, let me just simplify a little bit. This is minus plus, you can write it as 1. It's only fx then. And this one will be root 2 plus minus 1 x f dash x. So this can be written as f dash x over fx is equals to minus plus 1 over x into root 2 plus minus 1. Okay? Now, if I rationalize root 2 minus plus 1, so in denominator we will have 1 because a square minus b square is 1, so only x will be there. And this can be written as, if I take minus plus common, it is going to have 1 plus minus root 2 divided by x, right? Now, if I integrate both sides, we are going to have this is log base e fx, and this is 1 plus minus root 2 log base ex and the constant c. Now we have been given in the problem that f1 is 1. So let me use here, in place of x I am putting 1, so you are having ln f1, 1 plus minus root 2 ln 1 plus c. F of 1 is 1, so ln 1 is 0, so this is 0, this is 0, this is 0, implies c is 0. So we are actually having the equation like this, fx equals to ln x to the power 1 plus minus root 2. That yields fx is x to the power 1 plus minus root 2, correct? But now in the problem they have said that your fx is an increasing function. Fx is an increasing function. Therefore, your fx cannot be equals to x to the power 1 minus root 2. Because when x, the exponent of x becomes negative, then this function is no more an increasing function. So, since the function is an increasing, they have said, so we will say that our fx is nothing but x to the power root 2 plus 1. After doing so many things, we have reached to this conclusion that your fx is x to the power root 2 plus 1. Is it clear? What else in the problem? Okay. Okay. So, k is your f of n to the power root 2 minus 1. Achha, what about your f of n to the power root 2 minus 1? So in place of x, I'm writing n to the power root 2 minus 1 whole to the power root 2 plus 1. So that gives us, this is coming to n to the power 2 minus 1. So that gives us n only. Okay. So f of n to the power root 2 minus 1, we got this thing as my n. So I think our third part is already proved. So this part is proved, that f of n to the power root 2 minus 1 is nothing but n. Now again, f of n to the power root 2 minus 1 is k. Therefore, the given limit, what is the limit? This is the limit. Let me just copy this limit. Anyways, we cannot copy this. Okay. So limit n tends to infinity. Limit n tends to infinity. AK. AK means I have proved that k and n are same. Therefore, your AK is same as your AN. Divided by 2 to the power n minus 1. Now we have to find out this limit, and we have to find out the greatest integer value of that limit. Okay, now what else? Okay, can we prove I think I can prove this one, because I've already got my fx, right? I got my fx as, let me just prove this part also. Fx as x to the power root 2 plus 1. So what is f prime x? This is root 2 plus 1 into x to the power root 2. Now, what is f prime 1? That gives us root 2 plus 1. And we have been said to find out the value of tan inverse. We have to find out the value of tan inverse 1 over f prime 1. So that gives us tan inverse 1 over root 2 plus 1. That gives us tan inverse root 2 minus 1 after rationalization. Now the value of root 2 minus 1 that we all know is tan 22.5 degree, which is actually tan pi over 8. Therefore, this value will be tan inverse tan pi by 8. So that gives us pi over 8, right? So, second value, this one, we have already got its value, which is here pi by 8. So we are only left with the value of this limit. Okay. Now we have the recurrence relation. An plus 1 is an plus root over 1 plus an square. Okay. Now here we can see that we have to find out the limit of two sequences taken in the ratio. So we can think of Stoll-Cesaro theorem, which I have already done in day 1 class. Those who have not seen, link has been given in the description box. You can go for Stoll-Cesaro theorem in our day 1 class. Now for that we have to check that whether the Bn, the series Bn, which is actually your 2 to the power n minus 1, is an increasing sequence or not. And that is obvious as n is tending towards infinity. So as we move on, your B1 will be less than B2, will be less than B3, and this thing goes on, right? At the same time, when limit n approaches to infinity 2 to the power n minus 1, that is also approaching towards infinity. So now we are free to use Stoll-Cesaro theorem. It states that this limiting value, let me just denote it by L. So our L is same as limit n tends to infinity an plus 1 minus an divided by bn plus 1 minus bn. So that gives us limit n tends to infinity an plus 1 minus an. From this recurrence relation we get this thing as root over of 1 plus an square divided by bn plus 1. Your bn is 2 to the power n minus 1. So bn plus 1 will be 2 to the power n minus 2 to the power n minus 1. So that gives us limit n approaches to infinity root over of 1 plus an square divided by 2 to the power n minus 1. Am I correct? Okay, now how to solve this? Again, a new problem arises up. How to solve root over of an square, and we have been provided with a0 is equals to 0. That's it. a0 is equals to 0. Nothing else. So how to approach this? Okay, let me just go in the next page. It is limit n tends to infinity root over of 1 plus an squared divided by 2 to the power n minus 1. So how to solve this one? Now we have to get rid of this root over sign. To get rid of this root over sign, I will take help of trigonometry. We have been given that an plus 1 is an plus root over 1 plus an square. At the same time, we have been provided that a0 is 0. So to find out this sequence, I mean the numerator which is under root 1 plus an squared, I am going to assume that an is tan of theta n. Now why I have chosen tan theta n? Because 1 plus tan squared theta n will give us sec squared theta n. So automatically your root sign will go off. You can ask me one question at this stage, sir. If I take n as cot of theta n, will I get my answer? Absolutely will get your answer. There is no doubt about it. So if n is tan theta n, your a0 is 0, it implies what? a0 is 0, which is actually tan theta 0. That implies theta 0 is 0, right? And we are having tan theta n plus 1. From this relation I'm writing equals to tan theta n plus sec theta n. So if I simplify the right hand side, we are going to have 1 plus sine theta n divided by cos theta n, which is actually cos theta n by 2 plus sine theta n by 2 whole square divided by cos square theta n over 2 minus sine square theta n over 2. These are all submultiple angles. So which can be written as cos theta n over 2 plus sine theta n over 2 divided by cos theta n over 2 minus sine theta n over 2. And if we divide both numerator and denominator by cos theta n by 2, we are getting this thing, which can also be written as tan pi by 4 plus theta n over 2. So actually we got tan theta n plus 1 is tan of this. So we can write your theta n plus 1 is pi over 4 plus theta n over 2. Is this clear? Simple trigonometric application, nothing else. I have simply used the formulae and I have simplified it. Now, if theta n plus 1 is pi over 4 plus theta n, So what will be your theta n? Your theta n will be pi over 4 plus theta n minus 1 over 2. Again, theta n minus 1 can be written as pi by 4 plus theta n minus 2 over 2. Again, the same repetition I will go for. It's pi over 4 into 1 over 2 plus 1 over 2 square theta n minus 2. Now this theta n minus 2 again can be replaced by pi over 4 plus theta n minus 3 divided by 2. So that gives us pi over 4 plus half into pi over 4 plus 1 over 2 square pi over 4 plus 1 over 2 cube theta n minus 3, and this thing will go on. Okay, so simply by observing the pattern, you can say your theta n can be written as this thing goes on, a stage will come when this here it is 3. In the previous one it was 2. Now one stage will come when it will be n. So in that case your theta n will become pi over 4, 1 by 2 pi over 4, 1 by 2 square pi over 4, and this thing will go on. And the last one will be 1 over 2 to the power n minus 1 pi over 4 plus 1 over 2 to the power n into theta 0. Are you getting the point? Simply by looking the pattern, you can write what will be your theta n. So from here, if I take pi over 4 common, we are left with this GP series will be there. And the last one is theta naught by 2 to the power n. So this is your GP series. So I am applying the summation of GP series. 1 minus 2 to the power n divided by 1 minus half. And as we all know that theta 0 is 0. So this part will become 0. So now it is coming to pi over 2, 1 minus 1 over 1 by 2 to the power n, right? So we got your theta n as this one. Now, we have been given this one. So this limit now becomes limit n tends to infinity. This is basically 1 plus theta. An is tan theta n. So it will be sec theta n divided by 2 to the power n minus 1. So that gives us limit n tends to infinity. Sec theta n can be written as sec pi by 2 minus pi over 2 to the power n plus 1, right? Divided by 2 to the power n minus 1. Now sec 90 minus theta will give us cosec theta. So this is cosec pi over 2 to the power n plus 1 divided by 2 to the power n minus 1. So from here we can write limit n tends to infinity 1 over sine pi over 2 to the power n plus 1. Now as n is approaching towards infinity, pi by 2 to the power n plus 1, this part is tending towards 0. So what I will do is I will simply divide the thing by pi 2 to the power n plus 1 and I will simply multiply the same thing. Right? So this will go in the numerator. It will become, this will become limit n tends to infinity 2 to the power n plus 1 divided by 2 to the power n minus 1 into pi. And this part will become 1. as n is tending towards infinity. Correct? Therefore, we are actually having this thing as 4 divided by pi. Okay? Therefore, the value of this limit is approaching towards 4 over pi. Now, we have to find out, I have assumed that thing as L. So, we have written this thing as L. So, your L is coming to 4 over pi. But we need to find out the greatest integer function of L. So, greatest integer function of 4 over pi, that is going to be 1. Therefore, your option 1 is correct. Is it clear? Have you understood? So you see, in this problem, a lot of conceptions, 3-4 conceptions are hidden in it. Each and every conception is very, very important to solve the problem. So what I will suggest you, if you have understood the whole thing, you please try to do this sum again. And again you will face problem. The moment you face problem, you come back to the video and see the solution again. And that is the way of learning mathematics. Okay, so I hope you have enjoyed this class. See you on tomorrow and take a very good care of yourself. Thank you so much.